Do, re, mi, fa, sol, la, ti, do. That's a scale, albeit I did it pretty poorly. I tried to. When you look at a scale, a music scale like do, re, mi, fa, sol, la, ti, do, what you're doing when you go up that scale is you're changing the pitch of the sound you make. In other words, the note. Alright? A higher note, like this do, would sound squeakier, while this would sound really bass, like a low note like that. And the difference between those two sounds I made is called the pitch of sound. Okay? And the pitch, you could write it down, is the note on the scale that you play. And it's determined by frequency of the wave, of the sound wave. Alright? So, low pitch, high pitch. Alright? Low frequency wave, higher frequency wave. Okay. So, because the frequency determines the pitch of a sound, alright, that means that we can look at different hearing ranges, okay? And actually different animals have different ranges of frequencies or pitches that they are able to hear. So why don't you write down those hearing ranges real quick, and then we'll go through them, alright? So, humans can hear up to 20,000 hertz. Everything in the thousands of hertz is basically a sound that is very squeaky, alright? So, all these animals can hear some very squeaky sounds. You can't really tell the difference between 3,000 hertz and 5,000 hertz that much. It's very difficult to tell the difference, alright? Because when we speak, mostly we speak, I'll write this down, speaking is usually about, for humans, 120 hertz, alright? So it's near the bottom part of the range. But when I talk right now, that still means that my vocal cords are vibrating and pushing on the air. How often are they vibrating? Well, every second they vibrate 120 times. That's what hertz means. How many vibrations are in a second? And the wave that's going through the air makes each air molecule vibrate back and forth 120 times in a second. Alright? So these are high frequency waves. Alright? You can see dogs can hear much higher, 60,000, and elephants, because they're a large animal, are sensitive to lower sounds. Alright? They could go down to 16, actually. But they can't go as high as dogs or humans. Because dogs can hear very high, we've invented something also called a dog whistle, alright? Which usually average in, you could buy different kinds, but they average in about 35,000 hertz. That means we can't hear it, even though it is a very loud whistle. You could blow really, really loud into it. You might feel the pressure of the wave in your eardrums, but you're not going to hear sound. It's kind of a weird experience, alright? It's above 20,000. It's above the top. Dog whistles register in it above what we could hear, but not above what dogs can hear. So dogs still react to it, you know, as if they're hearing a sound, which there is a sound going on from them. Alright, so one more thing we should say about this scale that we did as well is you can write letters next to this scale. So another way to think of pitch, we said, is like the note you play. So we could do this next. We could start at A, B, C, D, E, F, G, and when you get back to the same word, do, there's no H in music. You just start back at A again. So this do is the same note as the do up here. They could both be A's, they could both be B's, but they're always going to be the same note in that scale. And going from one A all the way up to the next one, that's called an octave. Alright? An octave. And this A is actually double, the higher A is double the frequency of the lower one. So if you play a 100 hertz sound and you go up that scale, this one will be 200 hertz. A higher frequency, because that's what pitch is. It's frequency. Okay, let's draw waves of different pitches now. Okay, so I wanted to draw two waves for you here that have different pitches. In other words, different frequency waves. But they have the same volume. In the next video, you're going to study volume and how to draw waves of different volumes. But for now, same volume but different pitch. So these two waves, this is a low pitch one and this is a high pitch one. You can pause and draw them if you want and then continue. But these have the same volume but different pitches, okay? How do we know they have the same volume? The reason why we know that is volume, or sorry, loudness is another way to say that, is amplitude, okay? So these waves have the same amplitude, but this one is a high pitch wave, which means it has a higher frequency. What about that shape to you means that it's a higher frequency? Okay, good. If that were a water wave, you would have to push the water really frequently to make this wave. But this one, you just go not very frequently, right? And it makes a longer, more drawn out wave. So when there are more waves packed into a certain space, we say that wave is more frequent because there's just more of it existing every second, all right? So this one doesn't get taller, doesn't get a higher amplitude, it's the same loudness, but it is a higher pitch note because there are more waves squished and packed into that space, all right? While this one is more stretched out. So one thing we could say about a higher pitch wave here is we could say that it is more squished so there's more waves, and it's a smaller wavelength. So remember how to label the wavelength is to take a crest and a trough together and use that symbol lambda, and that's the wavelength. So this wavelength is very short because it's frequent, and this wavelength is very long or low pitch right there. All right, guys.